In addition, brine pools are regions of high primary productivity. Food is scarce in the deep sea. The lack of sunlight means there are no photosynthesizers like plants or phytoplankton to generate energy.
What if the deadliest lake on Earth wasn't on land, but hidden at the bottom of the ocean? Scientists finally reached this impossible place, expecting to find water. Instead, they found what looks like an underwater lake so lethal that almost nothing survives after crossing its shoreline. No explosions, no monsters, just silent water that turns life into death within moments. But before we reveal what really lies inside this terrifying underwater lake, take 1 second to hit like and unsubscribe, because discoveries this unbelievable deserve to be seen. At first glance, it makes no sense. Thousands of feet beneath the ocean's surface, where sunlight has never reached, there's what appears to be a real lake with waves, a shoreline, and even ripples. It looks strangely calm, almost inviting. But the moment anything enters it, everything changes. A robotic explorer lowered into the strange water began behaving in ways scientists had never expected. Creatures that drifted too close didn't swim away. They simply stopped moving, as if time itself had frozen around them. Their remains stayed preserved on the lake's edge, creating a haunting boundary between life and death. This isn't a movie scene or a computer-generated illusion. It's a real place on Earth's seafloor, captured by deep-sea submersibles and studied by some of the world's leading scientists. Nothing about this place should exist, yet every new expedition uncovers something even more disturbing than the last. The deeper scientists looked, the stranger the evidence became, and what they discovered next turned one of the ocean's greatest mysteries into something far more terrifying. To understand how strange this place really is, you have to go down there yourself. The trip starts normal enough: sunlight, blue water, the usual business of the upper ocean. But the deeper a submersible sinks, the more the world gets stripped away, one color at a time. First, it's the reds that vanish, swallowed within the first few dozen feet. Then the oranges, then yellows. By the time you pass 1,000 feet down, green is gone too, and the only thing left is a deep, suffocating blue that eventually gives way to absolute black. The sun isn't dim down here, it isn't distant, it simply doesn't exist anymore. It's a memory. Keep sinking. 2,000 feet, 3,000 feet. The pressure outside a research submersible's titanium hull is now crushing down at over 1,000 pounds per square inch, enough to turn an unprotected human body into pulp in seconds. The water hovers just above freezing. Outside the viewport, there's nothing but a flat, grey, endless desert of mud, stretching in every direction, lit only by the sub's own floodlights. This goes on for miles. Nothing changes, nothing moves. It's less like exploring the ocean and more like drifting across the surface of a dead moon. And then, without warning, the mud just ends. The floodlights catch something that shouldn't be possible this far down. A shoreline, a beach, a body of water sitting inside another body of water, with its own ripples, its own gentle currents, a thin mist hanging just above the surface like early morning fog. In the control room above, on the surface ship, the scientists watching the video feed go quiet. Every instinct in the human brain is telling them they're looking at a quiet lake at dusk, somewhere on dry land. But the depth gauge says otherwise. 3,000 feet. No land for miles in any direction. Just an open, rippling lake sitting at the bottom of the sea. Researchers who first found pools like this called them exactly what they looked like: lakes of the deep. But the more they studied them, the more the name stopped being charming and started being a warning. The optical illusion. Here's where it gets genuinely strange. The water inside this pool isn't just salty seawater sitting in a dip in the sea floor. It's a completely separate body of liquid, so dense with ancient dissolved salt that it refuses to mix with the ocean surrounding it. Where the two waters meet, something called a halocline forms, a sharp, visible boundary where salinity, and therefore density, changes almost instantly. And because the brine and the seawater bend light differently, that boundary becomes something you can actually watch happen on camera. It looks like a thick, syrupy film sitting on top of the water, warping and rippling like heat shimmering off summer asphalt. Except this is 900 feet underwater and pitch black outside the lights. Push a robotic arm down through that boundary, and the picture on the monitor distorts. The arm appears to bend, fracture, and snap out of alignment, as if it's punching through a pane of liquid glass. It hasn't broken. The light has. The pool even has its own internal wave system. Small, slow-motion swells rolling across its surface, driven by deep ocean currents passing overhead, curling and breaking against the shoreline in near-silent slow motion. And that shoreline isn't sand. It's a hardened, dark crust built from mineral deposits and the compacted shells of untold numbers of dead organisms rising slightly above the sea floor like the retaining wall of an infinity pool. Step back and take in the whole scene, and it's honestly beautiful, calm, almost peaceful, which is exactly the problem. The kill zone, chemistry of death. Because underneath that calm surface is one of the most efficient natural killing mechanisms on the planet. Start with the salt. Ordinary seawater carries about 35 parts per thousand of dissolved salt. The water inside a brine pool like this can run up to 5 times that concentration. When a deep-sea crab, an eel, or any unlucky animal crosses that boundary, its body's internal chemistry, carefully balanced for normal seawater, gets violently overwhelmed. Osmosis does the rest. The insanely salty water outside the animal's cells starts yanking moisture out of them, trying to equalize the imbalance. The cells collapse and dehydrate in seconds. At the same time, a flood of sodium and chloride ions rushes into the bloodstream, scrambling the nervous system's electrical signals. The brain can no longer talk to the muscles. The heart stutters, then stops. The animal goes rigid, not dead from drowning, but from total systems failure, in under a minute. And salt is just the opening act. Bubbling up continuously from deep cracks in the seafloor below is a steady stream of hydrogen sulfide and methane gas. For any gill-breathing creature, hydrogen sulfide is a fast, aggressive neurotoxin. It binds directly to the iron in hemoglobin, blocking the blood's ability to carry oxygen at all, meaning even if an animal manages to swim back out, the damage is often already done. It's not drowning, it's chemical suffocation, working from the inside out. So an animal that misjudges the edge, or gets caught in one of the pool's slow internal waves, doesn't sink and rot the way it would anywhere else in the ocean. Its muscles lock instantly into rigor. It stops moving mid-stride, and it sinks, not fast, but in eerie, weighted slow motion, down to the floor of the pool. And then something even stranger happens, or rather, doesn't happen. Nothing eats it. The graveyard. In a normal patch of ocean floor, a dead animal is a resource. Scavengers show up within hours. Bacteria finish the job within days. Nothing organic sticks around for long. The ocean recycles its dead almost immediately. Inside a brine pool, that entire system breaks down. The same conditions that instantly kill a crab or an eel, zero oxygen, crushing salinity, a chemical soup thick with toxins, also make it physically impossible for ordinary marine bacteria to survive. No oxygen means no decomposition. No decomposition means nothing ever really disappears. So the floor of the pool becomes something closer to a museum than a graveyard. When researchers finally got a clear camera pass over the bottom of one of these pools, what they found stopped them cold. Thousands of crabs, eels, and isopods lying exactly where they died, sometimes for decades, sometimes for centuries, their shells intact, their coloring barely faded, their limbs still articulated in the exact positions they were frozen in the instant they died. Not skeletons, not rotted husks, preserved, pickled by salt, in a process not far removed from how ancient bodies have been preserved in peat bogs, or the way Egyptian embalmers once dried out their dead on purpose. Around the outer rim of the pool, where the toxic brine bleeds gradually into normal seawater, this graveyard becomes visible as an actual physical ring, a boundary line of bodies marking exactly where the danger begins. Scientists call it, bluntly, the graveyard rim, and that rim isn't entirely lifeless. It attracts opportunists, giant deep-sea isopods and hagfish that patrol the edge, using smell to detect the preserved bodies just past the boundary. Every so often, one darts in, grabs a mummified carcass, and pulls it back out into safe water before the brine can claim it too. It's a strange, high-stakes form of scavenging, stealing meals from the edge of a trap that's already sprung. Even the physics of sinking down here is unnatural. Because the brine itself is so dense, it behaves less like water and more like a thick, heavy syrup. Bodies don't sink so much as slowly drift downward, resisted the whole way by the density of the liquid around them. Equipment lowered into the pool needs to be specifically weighted, or it simply won't break through the surface at all. It will float, suspended right on top of the halocline, unable to sink into the water below. It's a vault, sealed by chemistry, guarded by density, and stocked with a perfectly preserved body count that's been accumulating for longer than most human civilizations have existed. Ancient origins, how it was born. To understand how a killer lake like this ends up sitting at the bottom of an ocean, you have to go back roughly 150 million years, long before there was a Gulf of Mexico at all. Back then, the supercontinent Pangaea was tearing itself apart. As the continental plates pulled away from one another, a deep basin opened up between what would eventually become North America, South America, and Africa. That basin would one day become the Gulf of Mexico. But at the time, it wasn't an ocean at all. It was a shallow, isolated, landlocked sea, baking under an intensely hot, prehistoric sun. Every so often, shifting sea levels or tectonic movement would seal off the narrow channels connecting that basin to the wider ocean. Cut off from any fresh water supply and exposed to relentless heat, the trapped seawater simply evaporated. As it disappeared into the air, the dissolved minerals left behind became more and more concentrated until eventually the water couldn't hold any more salt, and sheets of solid crystalline salt began settling onto the basin floor. This cycle repeated. Flood, isolate, evaporate. Flood, isolate, evaporate. Over and over for millions of years, laying down layer after layer of pure salt, until the deposit beneath the basin reached an almost unbelievable thickness, in places up to 5 miles deep. Eventually the basin reopened permanently to the world ocean. Cold, deep sea water rushed in. Rivers from the surrounding continents began dumping sediment on top, sand, mud, and organic debris, layer after layer, for tens of millions of years, compressing under its own weight into solid rock. Here's the twist that makes everything else possible. Buried rock salt, under enough pressure, doesn't act like a rigid stone. It behaves almost like a slow-moving plastic. Geologists call this salt tectonics. As the immense weight of the rock above pressed down, the buried salt beneath it started to flow, squeezed like toothpaste, searching for any weakness in the crust above to escape through. Over millions of years, that pressure pushed salt upward into massive underground domes, pillars, and ridges, cracking and buckling the rock layers above. Eventually, some of those salt formations broke straight through the sea floor and made direct contact with the cold, pressurized ocean water above. The moment that happened, the exposed salt began dissolving. But because it was emerging into deep pits and depressions on the seafloor, the resulting hypersaline fluid had nowhere to escape to. It just sat there, too dense to mix, too heavy to rise, pooling inside the very craters left behind by the collapsing rock above the salt dome. That's the exact birth story of a brine pool, a subterranean fault line still actively pushing 150 million-year-old salt up into the modern ocean floor, dissolving it into a self-contained, self-sustaining pit of toxic water. And it explains the deadly gas, too. The same ancient basins that trapped all that salt are also extraordinarily efficient at trapping fossil fuels. Millions of years of buried organic material, compressed and cooked under the salt layer, transformed into vast underground reserves of oil, methane, and hydrogen sulfide, locked away because salt is nearly impermeable. But once salt tectonics fracture a pathway to the surface, those pressurized gases finally have somewhere to go. They rise up along the edges of the salt domes and dissolve straight into the brine pool above, turning simple, salty water into an active toxic cauldron. In a very real sense, every brine pool on Earth is a time capsule. The water is modern. The chemistry inside it, the salt, the sulfur, the trapped gas, was sealed away back when dinosaurs were still walking on dry land, and it's only now, 150 million years later, being slowly squeezed back out onto the modern sea floor. The human risk? Exploring it. Studying something like this from a control room miles above the surface is one thing. Actually flying a machine into it is another. Remotely operated vehicles sent down to study brine pools are worth millions of dollars, packed with delicate sensors, high-definition cameras, and precision robotic arms. And every single piece of that equipment is a target the moment it crosses the halocline. Start with the density. Push a robotic arm into brine that's roughly 5 times saltier than normal seawater, and the resistance isn't subtle. Pilots have described it as forcing equipment through thick syrup. Thruster dynamics change completely inside the pool. Push too far, sink too deep, and there's a real risk of getting the vehicle physically trapped in water too dense to escape from cleanly. Then there's the chemistry. The same hydrogen sulfide and methane bubbling up through the pool are highly corrosive. The instant a vehicle's hull breaks the surface of the brine, those gases start attacking metal seals, electronic housings, and exposed sensors. Leave a vehicle in there too long, and you risk permanently damaging cameras, frying internal electronics, or corroding the mechanical joints that keep the whole machine functional. So pilots have to thread an incredibly narrow needle, hovering with total precision at the very edge of the pool, fighting subtle internal currents and buoyant resistance, collecting samples and temperature readings as fast as possible, while staying just far enough back to avoid catastrophic exposure. And there's a darker risk hanging over every second of it. If a vehicle loses thruster power while hovering above the pool, it doesn't drift to safety. It sinks straight down into the graveyard below, joining the very same creatures it came here to study, preserved indefinitely alongside them. Every successful dive into a brine pool is, quite literally, Millions of dollars of engineering being gambled against one of the most hostile environments our planet has ever produced. And every single sample brought back up has in some way shattered a piece of what scientists thought they understood about biology. It's not alone. Brine pools around the world. Here's the part that should really unsettle you. This isn't some rare, one-of-a-kind anomaly. Oceanographers have now mapped dozens of these toxic pools, clustered in 3 main regions around the globe: the Gulf of Mexico, the Mediterranean Sea, and the Red Sea. In the deep trenches of the Gulf of Mexico sits the Orca Basin, the largest known brine pool on the planet, a staggering 21 kilometers long and 7 kilometers wide, an entire inland sea sitting at the bottom of the ocean, with salt concentrations nearly 8 times higher than the surrounding water. Farther east, buried deep in the Red Sea, is the Atlantis Too Deep, a brine pool actively heated by nearby magma chambers to temperatures exceeding 150 degrees Fahrenheit, a superheated pressurized stew loaded with dissolved heavy metals. Some are massive inland seas, some are barely a few feet across, dotting the seafloor like potholes on a neglected road. Different sizes, different regions, same underlying rule: total, absolute separation from the ocean around them. The paradox: life at the edge. And here's where the story flips completely on its head. Because for as deadly as the inside of these pools is, the very edge, that thin, volatile boundary line where toxic brine starts bleeding into normal seawater, is one of the most biologically active places in the deep ocean. The pool traps falling organic debris like a net, and along its rim, colonies of chemosynthetic bacteria gather to feed directly on the methane and hydrogen sulfide seeping out of the sea floor. These microbes don't need sunlight. They don't need oxygen. They build energy straight out of raw chemistry. And where the bacteria go, bigger life follows. Dense colonies of deep-sea mussels, tube worms, and specialized shrimp crowd along the shoreline, forming entire thriving ecosystems built on nothing but the same toxins that instantly kill anything that wanders a few feet further in. Death on one side, thriving, alien life on the other, separated by a boundary line you could cross in a single step. The bigger picture: alien oceans. And that contradiction is exactly why NASA cares about this place. Beneath the icy crusts of Europa and Enceladus, 2 moons orbiting Jupiter and Saturn, scientists believe entire oceans are sealed away under miles of solid ice. And they suspect the floors of those alien oceans might be shaped by the exact same forces at work here: fractured seabeds, escaping brine, salt tectonics squeezing mineral-rich fluid up from below. If life can carve out a foothold on the edge of one of the most hostile environments on Earth, a place with zero oxygen, extreme salinity, and a constant flood of toxic gas, then there's a real scientific case that it could do the same thing on a moon 300 million miles away, in an ocean no human has ever seen. Every time a camera crosses one of these haloclines, it isn't just filming a graveyard from the Jurassic Age. It's mapping the blueprint scientists are using to search for life across the entire solar system. A lake that isn't a lake, a shoreline with no beach, a graveyard with no decay, and somewhere past its edge, life finding a way to survive anyway. That's not fiction. That's the bottom of our own ocean right now, doing all of this in complete darkness. If this messed with your head, hit subscribe. The oceans got worse.